In this video, we're going to look at reaction mechanisms. And a reaction mechanism is a series of individual steps by which the overall reaction occurs. So you will spend a significant amount of time on reaction mechanisms when you go to organic chemistry. What we mean by reaction mechanism is, in principle, the same thing. It's the series of individual steps by which everything is happening. The way that we deal with them in Gen Chem is very different. We're not necessarily going to need to draw structures. We're not going to need to show where the electrons are going. But we are going to look step by step at how a reaction happens and then see if it is valid. So we'll have individual steps for an overall reaction. What we will do is just say, is this a valid mechanism or not? So, of course, best done through example. We're going to look at the overall reaction of H2 reacting with 2ICl to make 2HCl and I2. The proposed mechanism has these two steps. So in the first step, H2 and ICl react with each other to form HCl and HI. And in the second step, HI reacts with the other ICl to make HCl and I2. So in these two steps, right, you can imagine how these molecules would line up to form the products that are listed for each step. The sum of the steps, so if you take step 1 and add it to step 2, you get the overall reaction, which is a requirement. It's one of the things that you're going to have to check. And when we do this, right, HI, that wasn't in the reaction, but when we add this together, the HI cancels out. However, it was a necessary part of the mechanism. So without the HI, the reactions that are happening, right, there's no way to move the hydrogen and the iodine in the way that this is set up. So HI is something that we call a reaction intermediate. This is a species that forms in one elementary step and it's consumed in a later step. So it is something that we could isolate. So it's different from a transition state, but we don't have any at the end. We make it and then we use it in some later step. So what we will do is take the elementary steps, see if they add up to the overall reaction, and then see if they give a rate law that matches what we know the rate law should be. So there's a lot of information you have to be given in order to determine if a mechanism is valid, and this is how we will do it. So a reminder, you cannot determine a rate law from a balanced overall reaction. However, in an elementary step, you can use the equation to find a rate law for that step. So the reason that this works is because we're just looking at one of those bumps in the energy diagram, right? Every elementary step has multiple bumps. And in that step, the only thing it is showing you is exactly what is reacting in that step. So the rate law for that step can only depend on those things because those things reacting with each other determine the rate of that step. So what that means is that for our steps that we're likely to see, you could see a step where A just turns into products, and the rate law for this would be that the rate is equal to the rate constant times the concentration of A. So we're using the coefficients. It would just happen to be 1 here, and that's it. And we also define these or classify them with a molecularity. So this is a unimolecular step, meaning one thing just decomposes into whatever the products are for that step. We could have A reacting with A to make products, and now there are 2 of the A's So my rate is Ka squared. This is a bimolecular step. It's two things reacting with each other. They don't always have to be the same two things. We could have A reacting with B, and the rate law for that step would be rate equals K concentration of A times concentration of B, still bimolecular. We could have three A's reacting with each other and have that the rate is equal to Ka cubed. This would be a termolecular step. It's super rare. You're pretty much not going to have three things reacting with each other, especially now that you know about the collision model. The number of times that it took to approach the barrier when it was just two molecules that needed to line up with each other with the right energy in their collision to get over the hump, imagine adding a third. So if you had three molecules that had to line up perfectly to get over that energy barrier, it's the chances of it happening go way, way down. So we're really going to see unimolecular and bimolecular steps for something like this. In a mechanism, some of the steps are slow and some are fast. And the rate determining step is the slowest step that determines the rate of your reaction. So we'll abbreviate this RDS. It is the elementary step that is slower than all of the others, and it's so slow that it limits the overall rate of reaction to the point that it determines the overall rate law. So this is like that one slow spot in traffic that blocks everything for everyone else, and you are stuck behind whatever slow vehicles might be going because they are setting the pace. If you can't move past the slow thing, then that is determining the pace for everything, whether it's traffic or this reaction. So the way that this will show up, we'll look at it through this next example, which is NO2 plus CO reacting to form NO and CO2. In my mechanism, the first step is NO2 reacting with another NO2 to make NO3 and NO. This step is slow, and it will just say slow next to it in the labeling. Step 2 is when NO3 reacts with CO to form NO2 and CO2, and this step is fast. So step 1 determines the overall rate law and the overall rate of the reaction because it's slow. It's the rate determining step. This means that my rate law for this reaction from this mechanism is that the rate is equal to K times the concentration of NO2 squared. Now, this is just what I've written from the mechanism. The only reason that we can just continue with this is because it's consistent with experimental data. So we still have to take that rate law from the method of initial rates and see if it matches what we have for the mechanism. Now, what you are going to see when you do mechanisms later on is that you're getting a specific proposed path. That path matches the experimental data. That's where that path came from. So we can put an energy diagram together for this, and I mean, let's do it because we have two elementary steps. Let's show two elementary steps on an energy diagram. So energy versus reaction coordinate, right? Beginning on the left, ending on the right. My reactants have some energy. I have to get over that activation energy to get to the product of my first step, which has an intermediate in it. And then I have a second activation energy to get over for my second step to get to the full products. So, right, my intermediate is here. It's like a mini energy well. And the rate determining step, so the way that this energy is drawn, matches with what step is slow and what step is fast. So the slowest step has the highest overall energy. So on my full energy diagram, this is the tallest peak overall, right? That transition state um, point, that top of the activation energy barrier is the highest overall. Okay, so you can't prove a mechanism, and I will not ask you to propose a mechanism. However, given a mechanism, you can show that the mechanism is valid. Now, there are some other ways I could ask you this question. We'll bring that up, but in general, the skill that you will need to demonstrate is showing that a mechanism is valid. And the way that you show something is valid is one, check that the elementary steps add up to the overall reaction. And then two, that the rate law predicted by the mechanism is consistent with the experimental data. You must show that both conditions are met. So let's do this. We have our NO2Cl reaction, but the reverse of what we looked at in the collision model. We have the experimental rate law, which is that the rate is equal to K times NO2 squared. And we have a proposed mechanism. So two steps. The first step is slow, and the second step is fast. Let's see if this mechanism is valid. So the first thing that we check is that the steps add up to the overall reaction, and they do. The second step is that we see if the rate law determined by the rate determining step matches what we saw in the experiment. So from the rate determining step, which is step 1, my rate law would be that rate is equal to K times the concentration of NO2 times the concentration of Cl2. And this does not match the experimental data. So this mechanism is not valid. This is it for the problem. Add it up, yes or no. Now, if you add it up and the steps don't add up to the overall reaction, you don't have to go any further because you have a no immediately. Both things have to be yes in order for a mechanism to be valid. Okay, they're not all going to be this short, but let's do another example and let's switch this one up a little bit. So what if the first step is fast? So you have the reactants forming intermediates really, really quickly, and then the second step is slow. When this is the case, that first reaction, it will continue to go fast, but the products are going to build up, or the intermediates that are formed don't go through step 2 quickly. So step 2 is going slowly, so the concentration will build up so much so that they turn back into reactants. So anytime you have a slow step that's later in a mechanism, every step before it will be in equilibrium. So this also affects the rate and the rate law. So you cannot have intermediates in a rate law. And when the slow step is later, every time we write a rate law, we are very likely to have intermediates that show up from the elementary step, and we'll need to find a substitute for them. But the equilibrium makes it possible to find a substitute. So this is great. So is the proposed mechanism valid? We have 2H2 plus 2NO, making 2H2O and N2. The experimental rate law is that the rate is equal to KH2NO squared. And my proposed mechanism has a fast step. So it's an equilibrium. It may not be labeled as an equilibrium in all of the problems that you see, but you will need to treat it like an equilibrium. So I've got equilibrium arrows. This step is fast. The second step is slow. That's my rate determining step. And then step 3 is fast. So step 3, it will not be an equilibrium because it's just going to go, make the products. So I have also labeled my rate constants for the rate law for each elementary step on here. And in step 1, I have K1 and K minus 1. So the K minus 1 just means for the reverse reaction, where it's still the same reactants and products technically, but it's the reverse of it. You'll see why this matters in a second. Is the mechanism valid? Add everything up, and the reactions add up to be the overall reaction, so that's great. The rate law, from the rate determining step, the rate is equal to the rate constant. Now I've explicitly put K2. It's just going to be some constant in the end, but we're going to keep track of where these K's came from as we put everything together. Then times the concentration of H2 times the concentration of N2O2. Now N2O2 is an intermediate, so we have to find a substitute for it. You could look at this and say that it's not valid, but you actually don't have enough information because this rate law that has the intermediate in it doesn't represent the fully possible rate law, right? Something is determining the N2O2, and we have to put that factor in here. The thing that we use to substitute is the equilibrium step. So one of the definitions of equilibrium from way, way long ago at the very beginning of second semester is that equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. That is one of the definitions, and it's the one that we need, and it's super important for this. This means that the rate law for the forward reaction is equal to the rate law for the reverse reaction. So from step 1, I can write a rate law for the forward reaction that says the rate of the forward reaction is equal to K1 times the concentration of NO2 squared. And for the reverse reaction, the rate of the reverse reaction is equal to K minus 1 times the concentration of N2O2. And because it is in equilibrium, these two are equal to each other. So K1 NO2 squared equals K minus 1 N2O2. Well, concentration of N2O2 is what I need a substitute for. So I can divide both sides by K minus 1, and I have concentration of N2O2, which I can substitute into my rate law from the rate determining step to see what the rate law is based on this proposed mechanism. So I have that the rate is equal to K2 times H2, and then I'm going to plug in K1 over K minus 1 times NO squared. And K2, K1, K minus 1, those are all constants. So whatever they do, whatever they were, whatever we multiply and divide, all of that, we just have a constant at the end. So I'm just going to collect them all and call them K at this point. So my rate law from the mechanism is that rate is equal to K concentration of H2, concentration of NO squared. And this is a match. So we've now met the second condition. The mechanism is valid. So we have 1, we added everything up, check, yes. 2, the rate law from the mechanism matches the experimental rate law. So we are good to go.